Hey guys, what's going on? So, in this video, what we're going to do is try to establish a set of requirements for this bootloader. One of the primary requirements that I want out of this bootloader is for it to be robust, for it to have a lot of error handling, a lot of, or as much as I can conceptually apply, security features to the bootloader. And by any means, if you have any suggestions, please feel free to comment or join the Discord channel where I'm kind of tracking this project. And obviously subscribe to the channel. Okay, so I find that a lot of times when I'm doing a project, and if I get too far along into the project or the coding, then I don't even want to make videos just because I have to rewrite everything and to explain it, because I kind of prefer writing things as we go along and showing you in the videos, because I know exactly what's going on in my mind, as opposed to just going back and opening a file of 1,000 lines and just kind of just feeding you random lines of code all the time. So I kind of want to start documenting this early on before I get too far along into the code. And I've already gotten a little far in the code, but it's enough where I don't mind starting over and kind of showing you what's going on. But again, this video is going to be on just establishing some ideas and concepts behind this. And again, if you have suggestions or better ideas of how to do this, by all means, please do suggest them. This is my first time trying to write a real bootloader. And by real, I mean something that I would kind of feel safe of it being in a product. So let's get started with this. Okay, so what I'm going to show you here is the sort of order of operations, the things that I want the bootloader to do in some sort of sequential manner. Obviously, on power up, the first thing that should run is your bootloader, and it's going to have some sort of branching mechanism. It needs to decide whether it needs to actually update some new firmware that you're asking it to do, or if it should jump to the user application. So in scenario one, let's say that we want to load some new firmware. Well, it should be listening. The bootloader will be listening on either serial port, USB, Bluetooth, whatever mechanism it is that you're using to connect the bootloader or your device rather to the computer. That's what it should be listening through, whatever. That means that there should be some layer between the actual bootloader code and the code that listens on those ports, because this bootloader, I'm also intending it to be somewhat portable. So there needs to be some layer of abstraction between the actual bootloader code and hardware specific functions. Okay, and you'll see that as this thing progresses. So what is it listening for on whatever communication protocol we have? Well, it's listening for a secret handshake, something from the desktop that helps the device establish a session ID. What do I mean by that? Well, a session ID, first of all, let me tell you what it's going to provide. A session ID is going to provide a secure method for my microcontroller, or the bootloader rather, to know that it's talking to a safe device. Because anybody can just connect to our bootloader on the computer and start sending firmware. That's not something you want. You want the application that is sending the firmware to be a trusted application. So that's the idea of this sort of session ID mechanism. So the way I'm currently envisioning this is going to work is that the bootloader is going to generate a magic number, so to speak. It's just going to generate some 32-bit number or more, whatever, and it's going to send that number to the computer, to the application on the computer, and that application will run an algorithm of sorts. Okay, it cannot be a simple CRC32. It has to be something different, something unique. It can be a CRC32, but we also have to manipulate those numbers in some other way aside from the simple CRC32 itself, so that any party that's, let's say, sniffing our packets can't figure out what we're doing, right? If they sniff our packets and they see that we send a 32-bit number and then it replies with the same number, the CRC32 of the same number, that's easy to hack, okay? And that's what we don't want. So we'll generate a magic number. The PC will run some secret algorithm on it and return the result to the microcontroller in a header frame. The header frame will contain other information like the size of your firmware, the firmware that you're trying to flash, the checksum of that firmware, etc. And it will have the result of this secret algorithm thing. The microcontroller will then run the same algorithm on that random number that it generated. And mind you, the number has to be random that it generates, or as random as we can possibly get it, right? So if the microcontroller's result is the same as the computer's result, then we know that we've established a secure connection with a trusted application. And that is the basic idea of this whole session ID. And since it all starts from a random number that's generated, a random magic number, then every single time you connect to your bootloader and computer, will have a unique and hopefully different session ID. So that's the idea behind that. So I think that adds a level of security to this thing that we don't want just anybody being able to send us firmware. Okay, so that's that. So the other scenario is that once we're powered up and we establish a session ID, the other side of the coin, is that we don't establish a session ID or there is no app connected, right? Because the bootloader will always power up, always load on power up. So either we're going to bootload something or we're not. So if we're not, then obviously the next step is that we jump to the user application. This can happen. This could be like a sort of timeout. Maybe the bootloader will just wait 1 second or two. And if nothing happens, then okay, jump to the application. We can add some security measures here because we can check the vector table of the application we're jumping to. If the vector table does not exist, then we should not jump to the application because we'll just crash the microcontroller. And we can check the vector table of the application we're jumping to by checking for this value. This is the reset value of your memory addresses. When you erase your chip, this is the value that is written into all the addresses. So if we find a vector table that has all FFs on all the addresses, then, or even on one, or even especially the start of the vector table, then you've got a problem. So you should not jump to the application. Okay. So another thing to keep in mind is that how is the bootloader, let's say, this kind of goes along with this point right here, that the main app should have a mechanism to enter bootloader. So let me give you this scenario. So let's say the user application is running and then I connect the microcontroller to the computer and, the user application is still running, right? Okay. So I want to be able on the user application like this, for example, to just press connect and it should connect to the bootloader. That means in the actual application, in the user application, we should have some sort of mechanism where we're listening to see if a request to enter bootloader has happened. Another way to do this is just to use a button. Let's say you have a button on your device. You hold it for 2 seconds. If it's held for 2 seconds, that means we enter bootloader mode. However, when your bootloader loads, how does it know that it's going to bootload something? Or that it should stay in bootloader, right? Let's say I press the button on the microcontroller for 2 seconds. It causes a soft reset. It boots, but how does it know that, hey, I want to load firmware or I should stay in bootloader mode without you necessarily having to stay there and keep holding that button? So one way to do this is that you can use these backup registers. I know STM32 has backup registers for their RTC and some other tamper registers. These are registers that when you write data to them and you turn the microcontroller on or off, a soft power reset those values in those registers will stay there. Not a full power reset, unless it's actually backed up by the battery, unless you actually have a battery backup circuitry on your microcontroller. But if it's a full-blown power reset that it loses power, then the registers will be erased. However, if you're running your main application and you write data to these registers, these backup registers, and you do a soft reset where it doesn't lose power, it just resets the whole MCU via software, then those register values are indeed preserved. So what you could do is that when your microcontroller is running, and you connect to the PC, and it's still running your main application, and you send this sort of command to connect, what it could do, it could go to these registers. It could write a flag that says, hey, bootload firmware, or enter or stay in bootloader mode, or something like that, right? Whatever it is you need to write in there, you can do that. And then this part too, it also needs to not just accept any command from anything to restart into bootloader mode, right? Because we don't want that. What if this is not a trusted application? So this mechanism too needs to also have this sort of session ID or magic number thing. So we will not restart the MCU just because anybody tells us to. So that needs to also implement the sort of session ID. But what about this? What happens if I'm in my main application, I establish the main application, whatever I'm connected to, sends a proper session ID. I go into bootloader mode, but then I close that application and I open a malicious one once I've established a secure session ID, right? So that's bad, because now the bootloader thinks that, hey, I have a secure session ID, but I've actually closed that app and now I have a different one open. So then we have to do it again. So at least my idea right now is that to reset the device and get into bootloader, we need a secure session ID. Once in the bootloader, don't assume that we're still connected to the same app. So let's establish again, or reestablish, a secure session ID. Or at least, like I said, this is just a brain dump right here, this whole document. So I still have to think some things through. It could also be that maybe every single time that I do a command like erase or write or whatever, where I either erase firmware or write new firmware, I have to have some sort of security mechanism to know that I'm still talking to the same app. So this is definitely an idea that could be further developed. The whole idea here is security and not just trusting anything. Again, because establishing a session ID is great, but if in the meantime, I have one app open and then I close it, or I have another one, once I've established my session ID, how much does that help, right? Okay, so there's that idea. Let's see, bootloaders. Okay. This is another idea that I've kind of thought about, loading the bootloader functions into RAM, which should be able to speed things up, especially since the act of bootloading means that I'm going to write to flash. I just went over this about the mechanism that the bootloader should have. The main application should have a way of entering the bootloader. The header file that the bootloader or the application will send me should have a checksum of the entire image. And we should lock the unit if anything fishy is going on, so that we cannot write to it. If the microcontroller space permits, and if the user application is small enough, we can have two banks of firmware. One would be like, let's say, the current firmware that we're running, and the other bank would be the new firmware. So if the microcontroller gets a command to write new firmware, it'll write it to the bank that is designated for new firmware, right? So it'll write the whole application on that bank, and then the bootloader will then switch. It'll say, okay, now that I have new firmware in bank 2, then this becomes the quote unquote current firmware, and then this old bank will become the one where we write new firmware. So then when you have another command to write firmware again, then it'll write it to this one. And I hope you kind of just know that I'm just using this here for bank 1 and bank 2. So it'll just toggle back and forth between which is the new and which is the old bank, and write firmware depending on which one is currently being used as new. The idea behind that is to have a sort of fail-safe mechanism, right? Because let's say this is my current firmware. This is the bank where the new one will go. I get a command. I flash firmware to this bank, and even though the checksum and everything is fine, maybe there's just a bug in the firmware, and it keeps crashing my device. You can have a mechanism where you have a watchdog timer. Every single time your device crashes, you can write into one of these backup registers. And if you get like 5 or 10 crashes, your bootloader should say, hey, something's going on, right? Because your bootloader will always know what's going on because it's the first thing that loads up. So your bootloader will say, hey, I have 10 crashes. Therefore, there's something wrong with this firmware in bank 2. So I'm going to switch the current firmware to be this one. So it'll revert back to this old, good, known working firmware. So that's one idea behind that. What else was I going to mention here? Our packets, every single piece of communication back and forth between the microcontroller and the computer needs to have a frame packet. This is a very common sort of mechanism. I've seen it on the internet. I've seen it at work. It's this sort of, you have 2 delimiters, one to tell you this is the start of the frame and this is the end of the frame. You have something that tells you what kind of frame is this. Is this a command to write, to erase something? Is this a firmware payload? Whatever. Then this length field will tell you the length of this payload. So this can be any amount of length. I find that in my bootloader, this payload is going to be 16 bytes because when I'm sending firmware, I can only do 118 bits at a time. So sending more data than this is going to be pointless because I can't do it right away. So every frame that is being sent, even if it's new firmware, you're going to send start a frame, you're going to send a frame ID that says, hey, this is firmware, the length, which for example is going to be 16, and then in here is where you're going to put the actual bytes of your firmware, and then this CRC is going to be a CRC on this payload to make sure that it's correct. So when the computer sends the new firmware, it's going to send the CRC of this firmware. The microcontroller is going to receive this whole packet. It's going to read this payload, and it's going to do the CRC on it itself and see if it arrives at the same value that the PC got. And if it does, then it says, okay, I received firmware that, I mean, I don't know if it's correct. It could be a bug in your code, but at least I know that what the computer sent is the exact same thing that I received. And this is just so that the computer and the microcontroller know the start and end of frames. And this is simply just 4 bytes. It's an unsigned integer 32. This is 4 bytes. So this kind of leaves you room for like 4 billion, who knows how many different frame IDs. The length is, I've made it just 2 bytes. I don't really expect my payloads to be more than 65,000. At least at a given time. And then the CRC is also 4 bytes, and the end of frame is 4 bytes. And the payload, obviously, you can kind of decide what it needs to be. Another thing I was going to mention, which is now just slipping my mind, is... Okay, completely slipped my mind. I was going to say something about this, and I forgot now. But yeah, so any kind of communication back and forth between the microcontroller and the computer, they're both talking in sort of packets, whether it's an ACK or a NAC or a command to erase. Even the header file or the header frame will be a frame with header ID, with an ID that says header frame or whatever, and the payload will be the image checksum, the image length, how many blocks of data it should expect. Also, the the bootloader, if it receives an error, right? If it receives firmware payload and it does the CRC on it and it does not match what the computer said the CRC should be, then there was an error in transmission, right? So imagine you having a noisy system and somehow one of the payloads is corrupted. So then the bootloader will send a frame that tells the computer to retry. Hey, retry. But it's going to tell it what block number, because it's keeping track of each payload, of not the actual bytes, but each payload is a block. So it's keeping track of block numbers. So it's going to tell the computer, hey, retry block 4. And the computer is going to, have some sort of counter of how many blocks it sent. And it's going to go back to block 4. And it's going to restart from there and say, okay, so I'm going to start from block 4 again, resend it, and then keep moving forward from there. So this sort of retry mechanism definitely adds some sort of robustness. We can also add a sort of failed attempts. If we have 5 retries or more, then we can say, hey, this is not going to work out. Let's just stop. Or you can just make it keep retrying until it does pass or whatever. So yeah, so those are definitely some things to think about. This is the computer side of things, which I kind of already went over. But yep, that should kind of summarize the idea of what I want for this bootloader. Again, if you have any sort of suggestions, please feel free to comment, or I prefer if you join the Discord channel, just because I'm on that all the time, either at home or at work or on my phone. If you just comment on YouTube, then I have to go to YouTube. I have to log into my personal account if I'm at work, which I don't want to do that, and things like that. So yeah, or Instagram, whatever you guys want to message me on, but definitely the Discord would probably be the better way to go. Alright guys, that's going to do it for this video. I hope I was clear. If there's any ambiguity in what I said, please feel to ask questions or correct me, or if I just sounded dumb as hell, you're like, oh, this is the shittiest bootloader in the world, then by all means, just let me know. Alright guys, thanks.